Hey, what's going on, guys? CMK here. So the last video I've introduced you to the CMK Computer online emulator provided by Tinkercad. So let's try to enable this. So I just opened this in a new tab, and even though it seems like it's running on GitHub, on the real deal, this is just an iframe that loads the data from the Tinkercad project that I have there. But the benefit of doing so is that you don't really need to create a Tinkercad account in order to work with this CMK computer. So you can just go straight away using this direct link, and you're done. So you can already start the development. Now you need to click on this code button and on the serial monitor. So this is sort of the source code of everything that is flashed into the computer. It's written in C, but you don't really need this at all. So I recommend to make the serial monitor kind of full screen. So all you need to do here is just to put the program bytes here and then click the send button, assuming that CMK Computer is ready to receive the bytes. Now, the next thing I recommend is to maximize the size of the computer itself and place it like this, for instance, and finally click the Start Simulation button. All right, so CMK Computer boots into a hex editor, which means that from now on you can add the address followed by the bytes, and this would get flashed into the random access memory. So just to give you an idea, let's say I want to write some bytes to address 0000, and then I want to write some hexadecimal number. By the way, so all those keys match whatever is on them, a part of this too. So this is the hexadecimal E, and so the star is the hexadecimal E, while the hash symbol is the hexadecimal F. So this is how we can use E here, and this is how we can use F. So I hope it's clear. Now let's have a look at the commands available for CMK Computer in order to manipulate its behavior, basically. So the very first command I would like to introduce you to is clear the LCD screen. So if you type FFFA, this results in clearing the LCD screen. So let's give it a try. So FFFA, and now we have the clear command has flashed. So now we have just the clear LCD screen. This might be useful from time to time. And now the next command, so so we can inspect whatever we have in the memory. So FFFC shows 4 bytes in the memory at the entered address. So whatever address we want to expect for. So let's say FFFC, and I want to inspect the address of 0000, right? So here we have the program bytes that we've just input here. And for instance, if we say FFFC and let's say 0002, now you see like we have the 2 bytes from the previous screen, but the next 2 bytes are already zeros. And you can, the memory in the CMK computer is 1K of RAM here. Well, actually, there are 7 bytes after the RAM that holds all the registers that are involved within this computer: the A register, B register, the program counter, the stack pointer, and the flag. And well, technically, it's possible to manipulate those values as well, but I don't really recommend you doing this unless you know what exactly you're doing. Okay, so let's have a look at the next command. So for instance, if we want to reset the computer in the software way, let's say we can use the FFFB command. Now let's have a look how it works. So this would reset the entire memory and the state of the registers as well. So if I say FFFB, in this case, we get a software reset, and if we try to inspect the memory at 0000 again, we see like it has been cleared, okay? If you're using the LCD shield, though, it has the hardware, where is that? It has the hardware reset pin here, which connects to the reset on Arduino. It doesn't matter whether this is the Arduino Uno or Nano, because they are kind of pin compatible. So yeah, so when I'm doing this on the real hardware, I'm just pressing this reset button, which is like a bit better way of doing things, I believe. Just, yeah. Okay, so the next command to introduce is the run command, but in order to run the programs, you need to actually input the valid bytes here. But first, let me show you what happens if you just try to input, let's say I try to input exactly the same program. It's not a program, just the bytes, literally. But these are not the valid opcodes at any point. In this case, if I try to run the program, it would give me an error. So to run the program, we need to use the command FFFF, which stands for running the program. So if I say FFFF, so it just tells me that DE is the unknown opcode, and it's not the part of this list of opcodes. And every time when you see this unknown opcode error, this means that something has gone wrong and your program actually can't really be executed. So just to bear in mind this sort of a thing. All right, so the hardware reset in the emulator is done by stopping the simulation and restarting it again. And this is the preferable way of development, because like the hardware acceleration is really a better thing. Well, at least I recommend doing so. Okay, now let's try to, as you could have already seen, using this 16 16 numbering system, we can input machine codes in hex numbers, right? So let's try to write a simple program that displays the A character to screen. So in order to do this, so there are two ways of outputting the character to the screen. So the first one is this OUT command, and it outputs the character from the A register. So whatever we have in the A register, this would be flashed into the LCD screen. But there is another way to output characters, and there is the SPR, which stands for sprite. Where is that? SPR. Oh my god, yeah, here it is. So, and this, initially this is intended to draw the user-defined graphics, which is also available here. So LCD Shell allows you to work with the user, like to create the user-defined graphics to make the sprites basically. And then if you want to draw the sprite to the screen, you can use this command. But this can also work in order to display the instant character. So we'll start by this one because it's just easier to consider, and then we'll try a bit more sophisticated command. So let's kickstart with the SPR. So if I say 0, 0, 0, 0, for I want to write to the very first memory cell, and now the code for SPR is 1D. So if I just type 1 and D, and next I need to provide the ASCII character in hex. So for instance, let's try to type the letter A, and in this case we're printing the immediate data, so not something from the A register or something, but just the immediate data, and 61 is the code for the letter A. And then in order to kind of enter the string, as far as we don't really have the enter key here, we need to input up to 4 bytes in order to put this line into the memory. So the rest of bytes would be just zeros. And here we have our command being kind of input into the memory. Now if we try to run this by saying FFFF, it should print the letter A, which it does, right? So this is the first way of how to do things basically. And again, like another thing of doing well, if say you want to, so in this case you can do this dynamically, like incrementing the, so if you would be using the OUT, which prints the value from the A register, you can add a number to the A register, then use the OUT command, so it prints on the screen, and then you loop back, you add in 1 to A register, loop back, and in that case you can print all the ASCII characters, for instance, and that is one of the example programs I have for this computer, which we'll have a look at. But for now, let's just focus on, so just restart thin. For now, let's just focus on how this LDA works, like, LDI, load immediate data to the A register, followed by the OUT command. All right, so so this OUT, where is this? Yeah, this OUT relies on the value that is already stored, that has already been stored into the A register, right? So what we need to do is to store the value to the A register, and we're going to be using this instruction LDI, which loads the immediate data to the A register, and it has the opcode of 01. So 01, then the data that we want to load into the A register, and then this OUT. So let's give it a try. So 01, and the opcode for OUT is 0F. So if I simply say 0, 0, 0, 0, so starting from 0, and let's say 0, 1, and then what we want to load into the A register, well, let's try 62, which is the ASCII character B, the small b letter, and then 0F to actually output this to the screen, and to input this, the rest of bytes just zeros. And if I try to run this again, this should bring the letter B to the LCD display, which it does, and this works just like a charm. Okay, so now, as you could have already guessed, that the entire program can be entered using this keypad. So literally whatever program this computer can run, this can be entered using the keypad, but it takes long and it's incredibly unhandy to develop in machine codes directly, because the shifted memory addresses, and like you don't have then like a variable, because the variable is just the memory address, and by the time you're writing the code, the addresses shifts and the variables kind of like shift as well. So it's not really handy to do. So hence the idea of writing code somewhere else outside the computer, assembling the code, like turning this to the assembly mnemonics to the machine codes, and then sending the bytes that has been assembled via the serial port to the computer. And this is the next thing that we're gonna try here. So in order to make it work, if you didn't download the project yet, you really can do this by downloading or git cloning. Well, I already have the project here, and if I go to programs, and here we have the file assembler.py. But let's just open this hello.asm, the program that prints hello world, and I also open the terminal in the current working directory. And if I just simply say python3 assembler.py and hello.asm, what it does, it reads this program mnemonics, right? Then it tells you whatever label you've encountered, and it gives the address for every single label that you have encountered, right? So for instance, like the label might be either the place to jump the program counter to, or the instruction pointer if you're thinking from the x86 machine codes, x86 assembly language perspective. And also the labels might serve as the variable. For instance, here the print is just a label to jump to. So from here, and we just LPC stands for low program counter, we just jump here. And for instance, hello is just a variable here in this case, so we're loading the value at hello, and we also have the outside and the B register. I will cover this program just right in the moment, but just to give you an idea, the label might be either the place to jump to from wherever place in the program, or this might be the name of the procedure to call if you have the return statement after, or if you calling this as the subroutine, or alternatively, the label might serve as the variable. And whatever usage of the variable of the label you have, anyway, all the labels are assigned the values, and if you just add in the code or subtract or just getting rid of some part of code, the labels would get assigned automatically. And then every time you need to reference, let's say LDA hello, so instead of hello, there would be put address of this hello, right? So that's the very just essence behind why people actually invented assembly, because it's really easy and fast. It allows an easy and fast development as opposed to developing machine codes directly. So yeah, now let's break down. Well, before breaking down the program, let me first just show you how we can load the bytes into the computer. And then we'll have a look how this kind of source code works. Even though it's not the part of this tutorial, it's going to be covered in much greater details later on, but still. So all you need to do is to copy the program bytes. And now here you have an instruction what you need to do. So on CMK Computer, you need to type FFFD, which is the load command. Then either on Arduino IDE or in the simulator, you just need to open the serial monitor, copy and paste these bytes to the serial monitor, and then press and then click send, and then type FFFF on CMK Computer to run the program, and then enjoy the epic 8-bit computing experience. Okay, so let's give it a try. So here, if I just say FFFD, and oh my god, if you could ever imagine how many times I did this during developing this sort of a thing, yeah. my button on the mouse is gonna be dead soon because of that. Okay, so we just paste the bytes in, so it says like it's waiting for incoming data, so it's kind of stuck in the infinite loop until we get something in the serial port, in the serial buffer. So once I click send, it would start loading things. Okay, and it starts loading. And one little thing to bear in mind, that the speed of how this works in the simulator is really slower as opposed to the real hardware. So if you want to write some sort of a software that is intended to be run on the real hardware later on, you need to be thinking about the delays, because what works fine on this simulator would be light and fast on the real hardware. So this is another kind of limitation to bear in mind. But anyway, so once we get this done, we can already run the program, and let's actually do this. So let's say FFFF, and now whatever machine codes this program has been translated to are now getting executed by the CMK computer, which results in printing hello world letter by letter with a delay of 80 milliseconds, if I'm not mistaken. But obviously, we can inspect using the FFFC command that has been introduced already. We can inspect whatever bytes in the program memory. So you see, like 01, 00, 03, 02, and these are the exact bytes. So 01, 00, 03, 02. These are the exact bytes that we have pasted, right? And let's say we want to inspect the next 4 bytes. So if I say just FFFC and 0004, right? And here are the bytes. So 00 12 0012 0B 00, and these are exactly the bytes, right? So up to here to be exact, up to here, right? Nope, up to here. Okay, doesn't matter really that much. 00, yeah, like this. Okay. So, and up to the very end, even if you have a big, long program, all the bytes would be right in there, so you can inspect them using this FFFC command to provide the memory dump for a given memory address up to 4 bytes. You can inspect those as well. So sometimes it gets incredibly handy for debugging. So let's say you're sending the value somewhere in the memory and you want to inspect if that is the case, basically. So you can just navigate to that particular address. And these labels are very helpful. So for instance, you want to know what happens at the hello label. Right, so and at the hello label in particular, you have this byte 48, 65, 60, 60, and so on. So just to verify these bytes, so one of the reasons of why these labels are actually provided. So if we go to the address 0012 in hexadecimal, what happens is we see exactly what is there in the memory. So 0, 0, and 1, and 2. All right. And we have this 48, 65, 6C, 6C, which is exactly what we have at this label. So it's really like having the addresses for every single label helps you easily inspect the memory at the given memory address. So I hope it's clear, right? Well, now, I will demonstrate a couple more programs, literally all the programs I have so far written for this computer, including the Chrome dinosaur that has been introduced in the previous video. But first, let me very quickly walk through this assembly code. It's not a tutorial yet, so there would be detailed tutorials on how to code this, how to code in this assembly. This is going to be the topic of the next tutorials coming soon, hopefully. But just a bird's eye view of how the thing works. So just from the general logic perspective, let's say. So where is that the A register? So LDI 0x00. Just puts 0 to the A register. So yeah, we have 2 registers here in this computer, register A, register B. Then we have the program counter, which holds the address of the next instruction to execute. Also, we have the sec pointer, and for conditional logic, we have a 0 flag. So if you have a look at the source code of the CPU emulator, this can be found at the line number 145 in CMK Computer.ino here. So 2 registers, program counter, stack pointer, and the 0 flag. And that's pretty much all about it. So this is incredibly simple, but yet powerful design, to say the least. Because, yeah, I don't really think this is going to be that powerful, but yeah, it is. Okay, and the memory is like memory size of 1024 bytes, so 1K of RAM is available. Now, another important thing before I forgot to tell you this, guys, like a few words on the memory map, because it's really important if you're actually trying to write some real software for this sort of thing. So it has the stack growing downwards, and the stack pointer initially points to the last byte in the RAM and grows downwards. So in hexadecimal, this is 3FF. Because the next one is 400 hexadecimal, which is going to be the next byte after 1024 bytes. Then we have the first 512 bytes to store the program instructions and variables, and the last 512 bytes are shared between program variables and stack. And this needs a little bit more commentary. So the way how it works internally, you see, like, we're not sending the binary data to via the serial code, but the ASCII data, and it takes 2 characters to encode a single byte. And the amount of characters, the limit of characters we can send by the serial port, assuming the incoming buffer, which is the memory array, is only 1K. So we can only say 1024 bytes, and this can be and this 1024 bytes are used. Every byte is used for encode an ASCII character representing a letter, for instance, right? And then we turn those what happens internally in the CMK computer. So it takes this ASCII encoded bytes and transfers them to the integers, and that means that we have 1024 bytes of the ASCII characters as an input. And this results in 512 bytes of actual instruction bytes to execute by the CMK computer. So you can send a program bigger than 1K of ASCII bytes, and that's important thing to bear in mind. However, if you're courageous enough to type the program using the machine codes. So let's say you want the program that has like 700 bytes. You can input this using the serial port, but you can type this manually, and this would still work, because whatever you type from the keypad gets encoded dynamically on the fly. So in that case, you can extend the size of your program. So that might be kind of pretty interesting experience to consider. And the reason why this design solution has been made is just because of the timing of the serial port. Its timing is very important, because otherwise it just starts losing data. I didn't really manage to I was trying to encode the data on the fly, but this didn't work properly, and I was finding myself in a situation where like the bytes has been cropped from time to time, and not the entire program was loaded actually, and this was resulting in undefined behavior and was really incredibly difficult to debug. So eventually I've decided to use the built-in serial.read bytes instruction that just takes the number of bytes to read and the pointer to the array to read these bytes to, and I'm used memory and the size of 1K. So I read whatever ASCII characters are sent. I just read them into the memory, and then there is the routine that cleans that up. And as a little bit of a downside, let's say, so if you just have a look at this, let's inspect the exit. I just want to show you one little thing. So if we just go to FFFC and 0020, right? And let's even go a bit further on. No, what have I done? Yeah, unfortunately, if you type some crap, there is nothing else to do but just to restart the entire thing. But I just wanted to show you that after your program, there might be some random bytes that are there because of this algorithm of turning the ASCII bytes into the integers. So you need to bear in mind that you need to initialize whatever part of this 1K memory, because it really can have some random values. Okay, so just very quickly to demonstrate what am I talking about literally. So just copy this one and just paste this in and send. And I just want to have a look, where is, so exit 20, 21, 22, 3, 4, 5, 6, 7. Yeah, let's start from 27. So FFFC 0027. Yeah, and you see like this, D0, 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 D0. So these are already like these bytes don't do anything, they don't mean anything, but that's the side effect of converting the ASCII bytes to the integers. So so the program should end somewhere at so let's inspect, for instance, 0025, for instance. Yeah, so the last byte is 1E 1E00, so 1E00, and then we have this D0, D0, D0. So, well, anyway, program terminates here when it encounters 0. It would reset the stack pointer, so and it would be pointing to the very first instruction again, and this allows you to run the program multiple times, and you just need to ignore these bytes. If you want to use the memory filled by these D0 bytes, you just need to manually reset them within the program. So that's a little bit of a downside, but that's the trade-off behind the design solution. Okay, so let's try to run this again. So just to demonstrate you this, so it prints the hello world, and you might be wondering that the program counter would now point to the very last instruction, and we don't reset it. However, we do reset it. So when it's encountered the zero terminating byte right over in here, it actually resets the program counter automatically. So if I say FFFF one more time, it would just start running exactly the same program from start, and just runs the same program again. So you can run exactly the same program like infinite number of times. All right, so let's get back to our code. So we reset, so we load the instant value of 0 to the A register. It's not obvious because it loads, when it loads it's already 0, but just for clarity, just for didactic purposes. Then tab stands for transfer A to B, so it transfers the register, transfers the value of register A to register B. And now both registers are equal to 0. Well, again, at the program start, they are always equal to 0. But just for clarity, I've added these two lines. So these two lines resets the registers A and B. And then this is the loop to print the hello world string. So interesting command here is LDA. So it loads byte at hello. So it like by this byte 48, but not just at the memory address, but it also uses the in order to loop over these bytes, I'm using the offset, which is stored in the B register. And if we have a look at the LDA instruction in particular, so load data from memory address with register B offset to A register. So whatever we have at the memory address plus the B register offset, so this might be treated as the memory address indexed by the B register for easier understanding from the high level languages perspective. So whatever we have at the memory address indexed by the B register, or memory address plus the B register offset, that's literally the same. So whatever we have there, that value, that byte, the value of that byte would be loaded in the A register. So for instance, here the A register is equal to 0, the B register is equal to 0 as well. So LDA would load the byte from hello plus 0, because B is 0, and hello plus 0 is the address of this byte, and the absolute address for this is actually 0012. So the first time LDA instruction fires, it loads the value from the address 0012. Okay, so far so good. Then we're comparing this with a 0. So if we have the 0 terminating character, we just jump to the exit of the program. But this is not the case so far. Then this delay makes this nice cute effect of not flashing the entire string, but just like flashing letter by letter. And then this is most essential. So we increment the B register by 1 to increase the memory offset by 1 as well. So what happens after this? and then we just LPC is just a jump. LPC is just a low program counter. It stands for low program counter, and this is just an unconditional jump. So LPC print brings the program counter back to the print, and the next time it executes LDA hello, what happens? It actually would be memory plus, and B after inc is already 1, not 0 but 1. So after LDA hello would result in loading this byte, and the next iteration would be loading this byte, and the next iteration would be loading this byte, and so on. Because every time we make this loop, we have this increment for B register by 1, and hence LDA hello would be resulting loading the next byte. If you want to store the bytes in a loop like this, the STA command, the STA instruction does exactly the same, with the difference that instead of loading the value to the A register, it actually stores the value from the A register to whatever memory address plus the B register offset. And all of this thing that I've just said is documented here in this operation code's assembly mnemonics. Okay, so this is how we walk through all the bytes until we encounter 0 here, and if it is 0, then the 0 flags get set to true, and this jump is the conditional jump. So if 0 flag is equal to true in this case, we just jump to this exit label, and what it does, it just adjusts the cursor position. So this pause command sets the cursor at positions A and B, where A register stands for a call and B register stands for a row. And yeah, here there are kind of various things. So actually 01 might be the case, 02 might be the case as well. I don't know, for some reason in the documentation I saw 02 to put this to this to put the cursor to the second line in the LCD shield. But literally this is literally when we have just two rows in the LCD, so it starts from 0. So row 0 is the first row, row 1 is the second, row 0 is the first line, row 1 is the second line. Call 0 is the first call, call 1 is the second call. That's exactly like arrays or index in C, for instance. So yeah, it's probably be more accurate to say to have this this sort of a thing. And so here we just set up the value in A register and transfer into B register. So this is the way how we can init the value in the B register. So B register after this is equal to 1. Then we make A register equals to 0. And eventually we have, after calling the pause, we put in the cursor at 0 and 1. So call 0, row 1, and this actually puts the cursor, as you can see here in the simulation, puts the cursor here. So if you're not doing this, you just leave the cursor right over in here. So it's just a way to mimic this kind of new line thing. And yeah, let's actually try to use this bytes again, and I just stop the simulation, run, paste, and send. Oh well, that's crap. I'm sorry. I shouldn't be doing this. So first, obviously, right, and then like this. Okay, and this should be exactly the same thing. And yeah, the cursor should still go here after printing the string. All right, which it does. Okay, fine. Okay, so now let's just as a matter of practice, let's try to load a couple more programs into the emulator. And this is going to be it for this tutorial, and starting from the next one, we're going to be learning how actually to code in this assembly. So the next two programs I have here are the scroll program, which scrolls the all the ASCII characters along the screen. This is inspired by the Apple I computer test program, by the way. Just the order of scrolling is horizontal, while on Apple I it was actually vertical. And then we'll run this epic DINO, Chrome DINO game, which I've been demonstrating on the real hardware as well. So let's have a quick look how this works. So here I just say scroll ASM, right? And here are the program bytes. So the story is absolutely the same. So, well, I recommend to reset to make the hardware reset, even though FFFB also could have worked, but I recommend doing this hardware reset. So FFFD to load the bytes, paste the bytes in, send, wait a little bit, and then FFFF to run the program. So FFFF, and we run the program, and here we have this ASCII characters being scrolling along the display, and this is going to last forever basically because it doesn't have an escape condition. So in order to escape from this, you just need to make the hardware reset. So yeah, it's left to the user whether you are allowed to escape from the program or not, or you just want to reset. So that's pretty much all about it. Okay, and the very last thing, yeah, so just to very quickly show you the source code. So here is the source code for scroll. So here is the source code for a scroll. It's even less for this program to scroll characters, right? And finally, let's run the Chrome DINO game, and you have a look at the source code of the Chrome DINO game. It's really bigger, and it takes up to 496 bytes and lots of labels here. So let's try to compile that as well, to assemble that as well. So here I just say DINO ASM, and we have tons of labels, all the addresses. So if you want to inspect something, you can enter this to the hex editor and inspect the values. And here are the program bytes. So quite pretty big program, and it's almost the maximum size of the program that you can write for this computer. So it was 512 bytes, that would have been the limit. For otherwise, if you want to write a bigger program, as been mentioned before, you can just manually assemble this. Well, by the way, actually the assembler won't allow you to go above the 512 bytes unless you just alter the source code of the assembler. But anyway, so then you can just try to go and manually input the bytes. But yeah, it's a little bit devastating, I believe. So let's now go for the very final test here, and I say FFFD to load the bytes and send the bytes, and now this takes ages to receive. And again, like on the real hardware, it works almost instantly, which is good news. And again, like when I was debugging this Chrome DINO game, I was really doing this on the real hardware just because it's faster, and I also have the shortcuts for all the commands that, so on the real hardware, by the way, what you can do, instead of typing this FFFD, FFFC, B, and so on, you can just use this shortcut commands for like left loads, select runs, up view the memory, down clear the screen, right save the program, and reset is the hardware reset. So these shortcuts are really handy if you have this sort of a thing here. Right, but anyway, so we're done loading, and now let's try the epic experience of Chrome DINO running on CMK Computer. And here it asks you if you're ready, and it's controlled by the 0 button. I just programmed it that way. So 0 is to start the game and to jump, and you really need to press your mouse hard to actually make a jump, and there should be a delay. And yeah, on this emulator, it's really buggy. Sorry, not buggy, it's just it's quite slow, so it works much faster on the real hardware, but that's the downside of the emulator. Well, if you hack through the source code and remove the delays for scrolling, in that case you could have actually come up with a little bit faster version, and let's actually try to go for that. Why not to do so? Just a very quick, so this was somewhere in the update world, so let me just update world. Or I would rather just search for a delay directly. So delay, yeah, here it is. So for instance, if I just get rid of this delay entirely and recompile it again and copy and stop the simulation and start again and load the bytes. Oh man, what have I done? I'm sorry, just been in a hurry because the video is lasting too long, I believe. Yeah, so now this should be going faster because I got rid of this delay, but yeah, just store it back in the source code, so because this is intended to run on the real hardware. All right, and now it should be running actually faster. All right, now let's have a look if it is, like so. All right. Yeah, now it's running faster. I don't know if you can spot it, but yeah, I definitely can spot that this is now running faster. And this is how this is the speed of how, like, yeah, on the real hardware, like it runs around like with this sort of a speed. So yeah, feel free to hack around, and yeah, so you can play Chrome DINO, and yeah, and here is an unbeatable place for me. Okay, yeah, and just jump in here, hence the game over. And one more little trick that I've been demonstrating in the introductional video, so how you can hack through these games, how you can win the Chrome DINO game, a hack from CodeMonkey King. So you see like this, 0, 1, 2, or no, 0, 1, 2, 0, 1, 2, the third byte, or no, let me just inspect. It should be the fourth byte. So this byte, which is score, if we set this to somewhere close to FF, where if you reach the score of FF or in hex or 255 in decimal, you win the game. So if you manually hack this byte, in this case you can win the game. And let me demonstrate you this how this works. So if we say FFFC, and if we have a look at the address of 0000, so this byte is the score. So if we replace this byte with F0, for instance, then we'll start from decimal 240, something like that, 0072. So I just replicate the bytes that we have here in the beginning, and here I just say F0, for instance. And we got it in, and now we can run the game again. And now if we start, you just notice the score, and the score is gonna be, you see like the score is already significant. So once it reaches, yeah, so now you win. All right, but yeah, the downside is still prints that the game is over. Well, actually the game is over, but I just was too lazy to separate the routine to reset the map in order to start this from scratch the next time. So yeah, I just I was a bit lazy, so just reused the code partially. But if one would make some work around this, would be just and you win. Yeah, just a matter of separating the reset map routine to the separate subroutine, not using this as the loop as the label to jump to. But anyway. Okay guys, so this is kind of it from my side, and yeah, the very last thing to demonstrate is if we want to store, let's imagine that we've created a game or an app or whatever on this computer via inputting the bytes from the keypad, and we want to save our work. So now how this can be done, you can say FFFE, and it saves the bytes. And if I stop the simulation, if I don't stop the simulation, it would be scrolling forever until, and then it would just lose these initial bytes. So you need to make sure that you stop the simulation just right in time. And then you can just grab this program bytes, and they are exactly the same as those you have here, and you can save them somewhere in the txt file. And for instance, if you imagine a game with a state and with some sort of a state and the pause that would allow you to drop back to the hex editor for a while, then in theory you can save the what this save command does, so it's really intended more like for working with the real hardware. It's working with this simulator as well, but it's really intended working with the real hardware. So anyway, what it does, it makes the memory dump of the entire 1K of memory, and then you can restore the state of the previous session by just inputting this bytes in. But yeah, it's not really going to be working like that, because only 512 bytes are allowed to be the program instructions, so you will definitely need to split that half at very least. But well, anyway, so the idea is that this is how the computer interacts with the outer world. So you can just send the bytes that were like the memory, literally this is the memory dump that was in the memory in the CMK computer. You just dump it to the serial port, you can save it, and you can just pull it back, and that's pretty much all about it. So probably, yeah, sorry, just the very last thing to demonstrate. So let's just go back to our hello example, or even scroll example, because it just takes less space. So if I just start the simulation again, if I clear this, then if I load the scroll, and send it there. So let's imagine that we've just input this bytes by hand from the keypad, not from the serial port, but by hands. And we have some bytes in the memory, and we can inspect them. And I want to save our work. So I want to save our work. I just say FFFE, and I stop here. And just before this, D0, D0, D0. So all we need stops here. So 90 should be the very last byte we're interested in. Let me just quickly verify. Yeah. Oh, actually, no, it's 0900. Yeah, 090. So yeah, up to here. So these are the actual program bytes that, let's imagine we did input this using the keypad. So we can just copy this and then clear and then run it again. So for instance, we've saved this somewhere in the text file, like save this somewhere, and then we're taking it from here and want to restore the session or keep developing. So we just can plug it in, like paste it in, and I'm sorry, and FFFD, and these are literally exactly the same bytes, obviously. So yeah, we just paste them in, and we have exactly the same program being loaded, and we can still run it because these are exactly the same bytes. And that's the way how to interact with our world using the CMK Computer. Very minimalist way of interacting, just like Monkey Kane's interaction with the real world as well, by the way. Okay guys, so this is it from my side. So I hope you've enjoyed this introductional tutorial, and starting from the next video, we're going to be having an in-depth look at how the CMK assembly works. So how to, so what are the most common techniques for developing something useful in this assembly language. So it's like if the Chrome DINO is possible to be implemented here, then really lots of things can be done. And ultimately, I'm going to be writing a chess program to run this computer. This is going to be really challenging, and I'm going to be covering that on my chess programming channel as well. So yeah, we'll see how it works. I'm not sure yet if that actually works or not, but anyway. So this is it from my side, guys. Thanks for watching. See you in the next tutorials to learn how to code in CMK assembly. And until the next time, and take care.